Did that work?
I think it did.
Unmute. Can you hear me?
Yeah.
Yes, now we start.
Okay. You can see my email, right? So now I have to wait till this thing, or let me hide it somewhere. Okay. So we stopped here. So here is what you need to understand or take away from this part, Hussein. I think Hussein was the one who has issues with the mathematics or panicking from the mathematics. Okay, so I have X in general is a d-dimensional vector. So this is what do I have? I have D features. Yeah, this could be age, salary, I don't know, sex, and so on. Yeah, so I have d-dimensional vector. Okay, and I have, and I want to do some non-linear transformation of X into a Z space, right, of order Q. So I want to do a polynomial, transform X into a polynomial of order Q. Yeah? I'm not going to do the transformation. I'm going to use, right, a kernel. The kernel is going to look like this. The general form is 1 plus X transpose X dash to the power of Q. Yeah. So basically, you don't do the transformation, just use the kernel, right, to compute. This is equivalent to as if you did the transformation of X into the Z space of order Q, did the dot product between every point and another point. Yeah. Right. So this is equivalent to this because I have d-dimensional vectors, and this is right. So imagine you've done the transformation first. You'd have a very long vector, right, to do a dot product with another very long vector. Now you're saving this by doing dot product between shorter vectors, right, in the original feature space, so equal to d, length of length d, and just raising this to the power of q. The general form, right, in the libraries is as follows. So the polynomial kernel has a form of a x transpose x dash plus b to the power of q. Okay, so this is what you have in the libraries. You'd have, right, let's say I want to use support vector machines, and you specify the kernel, what type of kernel you're going to be using. Yeah, and oops, what happened? Okay, so you can use, right, a polynomial kernel. Where's the chat? Yeah, okay, which happens to be of this form. That's all you need to worry about. Okay. So how do I set A, B, and Q? Question for you guys. So I have, right, I don't know how. So if somebody asked me, how do I know the formula for the transformation, nonlinear transformation? And I told him you don't need to know it, right? You can try with different values and then see. So I have a data set, a training set, right? And I want to use support vector machines. And then, right, I have these, I'm going to use a polynomial kernel, right? Because the data is nonlinearly separable. And so I have to set A, B, and Q. And B here is, this B is different from the B, right? The threshold value, just part of the polynomial. How do I set these values, A, B, and Q? You should know. These are hyperparameters. How do I set hyperparameters of a model? Using?
Trial and error.
Trial and error. What is trial and error in machine learning? Using validation, right? So I have a validation set that I try on. Let's say I set A to 2, B to 3, Q to 2, and then try on the data set, right? Divide the data set into training, validation, and test. Train the support vector machine model with this kernel on the training data, and then validate on the validation. See what is your error. Yeah, so compute F measure or accuracy, etc. And then try with different values. A, another value A, another value B, another value Q, and so on. Yeah. in the new assignment, assignment 6, you will see a principal method for doing this called grid search. Yeah, so you do a grid, you build a grid of all the hyperparameters for all the hyperparameters that you have, set their values, and or set a range of values for them, and then the library automatically tries for you and gives you the best hyperparameters. Okay, so called grid search. There's also something called random search we'll look at when we do neural networks. Yeah, so you need to understand what are the hyperparameters of this model. That's A, the B, and Q. All right. Good. There's another common kernel called the radial basis function kernel. Again, just know it, right? You don't have to worry about the mathematics behind it. It looks like this. Exponent of minus gamma norm x minus x dash all squared. So you take 2 points, right? In your training examples, you said get the vector, do the vector difference between them, the norm of this vector, square, multiplied by a gamma, and then raise to the negative e to the negative of this value. What are the hyperparameters of this model?
Gamma.
Gamma, exactly, right? Gamma is the thing that you would have to try and do a trial and error to set the value of gamma. You can set it to 2, to 3, to 4, and see which one performs better. Again, using a validation set or using... Yes.
Sir, so now we have 2 kernels.
Yeah.
Which one do you like? This one only has 1 parameter. The other has like 3.
Yeah.
Unknown. So
yeah.
Which one do we use?
Again, you can try both, right? So you can try radial basis function with, or RBF kernel with different gammas. You can try polynomial kernel with different A, B, and Q, and see which one performs better on a validation set or using cross-validation. Yeah?
Yes.
So as if you're trying different models. Okay, so do model selection. Just a note on radial basis function kernel, it's equivalent to an infinite dimensional space. Yeah. A kernel could be any transformation. So it's not all, right? Not all kernels, right? So you cannot come up with any form of a kernel and say this is a valid kernel, right? It has to satisfy certain properties, right? Beyond the scope of the course. But they correspond to some transformation. Yeah, they correspond to some nonlinear transformation. We don't need to care about what is the nonlinear transformation. Yeah. So, for instance, the previous one, the polynomial one corresponds to a polynomial, some form of a nonlinear transformation of order Q. This corresponds to an infinite dimensional nonlinear transformation. Yeah, I can show you how, right? So I'll show you how, but this is a little bit difficult mathematically. So consider the simple case, you have only 1 dimension. So your D is equal to 1. So I have value X, basically, and gamma is equal to 1. So I get the kernel of X and X dash is just the exponent of minus X dash all squared. Yeah, the norm goes away because it's 1-dimensional data. The gamma is equal to 1, and yeah, so I get and the dimensions are 1. Yeah, okay. So this is equivalent to what? Exponent of minus x squared, exponent of e minus e to the power of minus x dash squared, e to the power of 2 x dash. I expanded this. Okay, I can expand using Taylor expansion. So this is e to the power of minus x squared, e to the power of minus x dash squared, summation from k equals 0 to infinity, 2 to the power of k. So I expanded this term using Taylor expansion. I hope you know. 2 to the power of k, x to the power of k, x dash to the power of k over k factorial. Yeah, where k is going from 0 to infinity. And now I can separate the terms, right? So I have 2 terms, an infinite series of 2 terms multiplied by each other. One depends on x, exactly the same, and one depends on x dash, exactly the same. Yeah, so this is equivalent to as if you did a non-linear transformation, right, of infinite dimensions. Basically, you have x to the power of 0, x dash to the power of 0, plus x to the power of 1, x dash to the power of 1. Remember when we did the nonlinear transform and then multiplied or did the dot product, we get something similar. Yeah? So just know that this corresponds to an infinite dimensional Z space, yeah, without really having to worry too much about the details. And the hyperparameter is the gap. Okay. So kernel K and x of x and x dash is some transformation Z. Yeah, we don't need to worry about what is the transformation. We just know that it's a nonlinear transformation Z. Right. Solve using the quadratic programming, right? Again, right? The library would, we don't have to worry about anything, right? The library would do this for you. But just a question for you. Before we had Q, right? Y1, Y1, Z1 transpose Z1. So we said we transform the point into the Z space and all the points into Z space and then do the dot product in the Z space. With the kernels, what do we do? What changes here?
The Z, we just change it to x's.
If we use axis, then
the
it's non-linear transformation. I want to use a non-linear transformation. So the Z's, yes, but what do I change the Z's into? What was the kernel?
x and x dash.
I changed it into the kernel, right? Yes, yes, yes. What did I? K of K, but not of Z, Z dash and Z. If I do K of Z dash and Z, then I already did the nonlinear transformation. So I didn't save anything. So the only difference, right, is I do Y1, Y1 of the kernel, right? Where kernel is basically going to be 1 plus X1, X dash, X1 dash, X1 transpose, X1. And then here, this one could be 1 plus X1 transpose X2, all to the power of 2, and so on. Yeah. So basically, you're just using the kernel. Okay, folks, to summarize, in the assignment, in assignment 6, I'll be asking you to do support vector machines. So I'll give you a data set of images, yeah, represented using using some numerical features. So I don't know how many of them, but I forgot. But you have a vector, right, of features, and then a label, right, which is from 0 to 9. So I think it's the handwritten digits data set, if I'm not mistaken. And then I'm going to ask you to use as support vector machines model on it. First, the linear one, yeah. And for this, you would have to see how, and of course, the data is non-linearly separable, so you'll see that the performance is really bad, or it will not, you know, will not give you any solution because the data is non-linearly separable. Is not linearly separable, and so then I'm going to ask you to use a kernel. Right, so to use a polynomial kernel and to use an RBF kernel. Yeah, so all you have to do is set these parameters. Yeah, so try with different parameters, A, B, and Q, or whatever the library provides you. So you might have different names in the library, and then run it on the data set, and then see what is the performance on the validation set. Do the same thing using RBF, right, by setting gamma or whatever the parameter is called in the library, and then see how it performs on the validation set. Okay, that's all you have to worry about in terms of the libraries, using the libraries. Yeah, you don't have to really, it's not complicated. You don't have to do any quadratic programming or show any build this matrix Q or anything. It automatically does all of this. All you have to specify is that you're going to use a kernel of this type.
Professor, are we going to have online session to solve the assignment together and help us with libraries last time?
Yeah. So we'll do that, right? So we can have another session on Monday, for instance, to help you a little bit with the libraries. And the solution of the assignments is usually done on Wednesday. Yeah. So Shadi yesterday did it? No? Did anybody tune into yesterday?
Yes, he did it, but عندي 253 class.
Okay. So I'll see if he recorded it or not. If he recorded it, I'll ask him to post the recording. If not, on Monday, right, I'll ask him to have another session similar to last week.
Deal. Yeah, thank you.
What? Somebody else was saying something? Yes?
Actually, I was saying thank you.
Yeah, you're welcome. Okay. Now, we have the following, right? So soft margin SVM, right? So this is nothing new, but this is how most of the libraries work. So you work with kernel, but it also works with something called soft margin SVM. So we have two cases of non-linearly separable data. Yeah. First one is severe. The second one is not so severe. So in the second one, this one, the data is almost linearly separable, except for some exceptions. Yeah, this one and this one. This one is seriously non-linearly separable. Okay, sorry. For the seriously non-linearly separable, we typically use a kernel, or the kernel would work better. For data like this, right, slightly non-separable, typically we use what is called a soft margin SVM. Okay. So what's the idea of soft margin SVM? You allow some points to violate the margin. Remember, where are the support vectors? These, right? So I allow some points to cross this margin. For example, this blue point, right? I allow it to be like this, right? To cross the margin. So the distance basically becomes not greater than or equal to 1, becomes, right, less than this. Right? In fact, the point can even cross to the other side completely. Hence, right, I can accommodate non-linearly separable data. Okay. So margin violation, how do I represent this? Before we had something like this. Yi W transpose Xi plus B is greater than or equal to 1. We didn't have minus eta I. So I add minus eta I. Let's see what this means. Right? This eta I is greater than or equal to 0. So it's a positive value, or 0. So why is this corresponding to a violation, margin violation? Because before the distance was at most 1, at least 1, right? Defined by these points, the support vectors. Now I'm saying the points can be, right, for some points, right, it can be less than 1. Yeah, so 1 minus eta I. Yeah, so this point would be a violation of the margin. It has a distance less than eta I, less than 1. Tuition is clear?
Sir, is the eta I is the number of points that are crossing this margin?
No, it's the amount. How much for every point? It's for every point you have an eta I. Yeah, and for every point it could be 0, meaning that the point do not violate the margin, or it could be positive, means that this point violates the margin. Yeah, if it's positive.
What's the difference between 1 and 2? Let's say.
So one means this is on the border, right? The blue point here, the red point here, the red point here. These are the ones. 2 means interior point, right? If it crosses the line, would it be bigger than 1? It would be no, it would be less than 1, right? Because eta is positive. So 1 minus positive value, that would be less than 1. So 1 minus, let's say, 0.3 would be 0.7. Does this answer your questions yet?
But I didn't get what do you mean. يعني, it's good to allow some points to violate the margin بس لحتى يكون عندنا this big margin.
Who's asking? Hussein? Can you repeat, Hussein?
Well, is it better to have to let some points violate the margin بس لحتى يكون عندنا this big margin؟ يعني مثل this blue point here. He violated the margin بس نحن عملناه هيك ما يكون عندنا thick margin الصفراء.
لا احنا كان عندنا before, right, it was like this. The data was like this, right? So I had this thick margin. I picked this hyperplane or line so that it's further away from the red points and the blue points as far as possible. So I have this thick margin, the yellow margin, right? Now I'm allowing some points to cross this margin. Why? So that I can model non-linearly separable data. So something like this, right? So now I allow some points to be inside this margin. Even though I have a margin, I allow some points to violate it. By how much they violated? By this amount, eta I. So before, right, it was like yi w transpose xi plus b greater than or equal to 1. Now it's 1 minus eta I, where eta I is a positive value.
Okay, I get you. Thanks.
Oh, somebody had a question. Ziad, if it crosses the line, wouldn't it be bigger than 1? So I said, right, it's a positive, so it would be less than 1. What is the maximum value of it? It means eta, it's a positive value, right? Can be anything. We'll see. We will see. We want to minimize it as much as possible, so we're going to put a constraint on it, but it could be, right, anything. But we want it as small as possible. We want to minimize the violations as much as possible. Otherwise, all the points would cross the margin. So the new optimization problem. Before it was minimized, half W transpose W, that's to maximize the margin, subject to yi, the things in red, in black, right? That was the original optimization problem. Now I add to this C, summation from I equal 1 to n, eta I. These are the violations. And I want to minimize these violations, right? The sum of these violations, I want to minimize them, right? The amount of violation, I want to minimize. Yeah? And now subject to what? Subject to that, right? This thing is greater than or equal to 1 minus eta I. And eta I is greater than or equal to 0 for every point I equal 1 to until. Yeah? So I only added this. I want to minimize the amount of violation. And now I allow violation in the constraints. Before it was strictly 1, now it's 1 minus eta I. So some points would have, right, this equal to greater than or equal to 1 when eta is equal to 0. And for some points, they would cross the margin. Okay? If C is too large, this is very important, right? The C thing is very important. That's a big parameter in support vector machines in the libraries. So you'll find the C, right? And unless you understand the mathematics, you will never be able to say, what is the C, right? Why is it important? So if C is large, very large, right? What am I trying to minimize? Is it the half W transpose W, the margin? So I'm trying to maximize the margin, or I'm trying to minimize the violations? I heard some type.
We're trying to minimize the violations.
We're trying to minimize the violations, right? So what does this mean? It means that I would not allow any violations, right? Do not make any violations because C is very large. So what does this mean? It's a hard margin SVM. Hard margin SVM means what? Means the linearly separate, assuming the data is linearly separate. So in the assignment to implement a linear SVM, you will have to set C, the parameter C, to a very large value. Yeah, when you set C to a very large value, this will imitate as if you're doing a linear SVM. Yeah, there's no linear SVM per se, it's all, or hard margin SVM, sorry. There's always soft margin. So the only one implemented is a soft margin SVM. So to imitate it, right, a hard margin SVM, you set C, the parameter C, to a very large value. Okay, and if C is too small, right, what would happen is?
It's the opposite. Sir, here we're just increasing C too much so that the ethas don't even appear, like we just...
Yeah, so you make them zeros all. Yeah, so
yes,
when you make C very large, the ethas have to be zeros in order to minimize this whole component. Okay?
And when
so
we
no
decrease it, it's the opposite. So,
yeah. So when C is very small, you allow a lot of etas, right? The etas to be positive. So a lot of points, you know, cross allow many violations, right? And you have a very large margin, but then so many violations. So it's useless. Yeah, because you're now minimizing only this value, right? And this will give you a very large margin, but then you're allowing so many violations. So it becomes useless. Yeah, so it's a trade. So how do I set C in reality? Using question. How do I set C?
Validation data.
Using validation data, exactly. So it's a hyperparameter, and I set it using validation data. Yeah. Okay. Right. So quickly, we're gonna do them some differentiation, and then we're done. So before, the optimization problem was like this. This is exactly what we did in the beginning, right? So I'm not gonna dwell into it. So before, right, we had this. Now don't forget that there is a component in the optimization problem or the objective function C summation from I equal 1 to n eta I. And I have, right, the constraint in the zero form. Before it was -1, now it's -1 plus eta I. And don't forget, right, that now the loss function depends on eta, right, like the values of eta. And I have to add a Lagrange multiplier for the eta. So minus summation from I equal 1 to n mu I eta I, like we did here, right? I have eta I is greater than or equal to 0. That's a constraint. So I have to do minus sigma from I equal 1 to n mu I eta I, like we did here in the 0 form. Okay, so now the loss function depends on W, B, eta, lambda, and mu. So minimizing this function with respect to W and B, and each eta I, and maximize with respect to lambda I and mu I. Yeah, because these are the original parameters, and these are the Lagrange multipliers. So I maximize with respect to them. I have lambda i's greater than or equal to 0. Mu i's, again, another Lagrange multiplier, so it's greater than or equal to 0. I have this, as we said, every one of these is equal to 0. And I have every one of these guys is equal to 0. Yeah, so these are the constraints that I have. Right. So how do I get the value of W in this loss function? What do I do? We differentiate and equate to 0, exactly. Where did mu come from? So mu came from, you had a constraint here. Remember that you had in the loss function, right? You had this, and you had this condition, eta I is greater than or equal to 0. So that's a constraint. So I add, right, to the loss function, similar to what I do here, right? So minus summation from I equal 1 to n lambda I, yi in the 0 form, right? This in the 0 form. I have to do minus summation from I equal 1 to n. Again, mu I, eta I, right? Because eta I in the 0 form, right? This constraint in the 0 form is just eta I. Okay? So that's another Lagrange multiplier for this constraint. Yes. So Rodriguez already told you Lagrange. Okay, okay. So I'm gonna differentiate with respect to L, with respect to W, and equate to 0. And I get surprisingly exactly the same thing as before. Why? Because, right, this doesn't depend on W, this doesn't depend on W, this doesn't depend on W. So I get exactly the same as before. When it's my thing with respect to B, I get also exactly the same as before. You can do the math, right? We're not going to repeat it, but I get exactly the same, right? Because the new terms that I added has nothing to do with B. So I get summation from I equal 1 to n lambda I yi is equal to 0. Now I need to minimize with respect to eta I. What do I get? Who can tell me? I have C minus
mu
minus lambda I minus mu I, right? 3 minus lambda I minus mu I is equal to 0. So that tells you the following, right? For every, the summation of every Lagrange multiplier lambda and mu is going to be equal to C for every data point that I have. Correct? You take this here, you take this here, their summation would be equal to C. Okay? I substitute back in L, and I get exactly the same equation as before. You can verify it offline, but I get exactly the same. Running out of time again. Okay. We're running out of time anyway. You have classes after? Anybody?
Yes.
And I don't.
You don't. Okay, we'll try to finish. So that you can do the assignment. If not, we'll continue on Tuesday. But I mean, everything that you need for the assignment is done now. Yeah. Okay, so the quadratic program, right? Again, right? I solved this. Okay, the only difference now is that lambda I is less than or equal to C rather than lambda I is less than or equal to C rather than infinity. Why is that? From this equation, right? I have C minus is equal to lambda I is equal to C minus mu I, right? And mu I is greater than or equal to 0. So in the maximum, right, the lambda I would be when mu I is equal to 0, it's equal to C. So its maximum value is C. That's the maximum it can get, right? So the lambda I goes here, and it's C minus mu I, and mu I, we know that it's a greater than or equal to 0. So the maximum value it can get is C. So only difference.
Sir?
Yes.
And the third one, last slide. Can you go back?
Yes.
Yes, here. When we substitute using the mu, why doesn't it appear in the last function?
Because you have C summation from I equal 1 to n eta I minus summation from I equal 1 lambda I eta I minus summation from I equal 1 to n mu I eta I, right? So you can take eta I common factor, you get C minus lambda I minus mu I, which is equal to always 0 from this equation. So it goes away completely. Yeah?
Yeah, okay.
Got it?
Thank you.
You're welcome. So the only difference again is that, right, the lambda i's are going to be bound by C. So instead of infinity having any possible value, it's going to be bounded by C. Okay. I solved the quadratic program. It gives me back some lambdas. I substitute in the equation summation from I equal 1 to n lambda I, yi, xi to get w. And then use, right, let's see the support vectors. Last thing, I promise. We have 2 more slides. So we have lambda I is equal to 0 or lambda I not equal to 0. Am I recording?
Yes.
Okay. Good.
Yes,
Okay,
it's recording.
Good. Fine. So before I had lambda I equal to 0, lambda I not equal to 0. If lambda I is equal to 0, I get that this second part would not be equal to 0. So I get yi w transpose xi plus b is greater than 1 minus eta I. Okay. And then I have 2 cases. Either mu I is equal to 0, mu I is not equal to 0. If mu I is equal to 0, okay, what does this tell me? Tells me it's not possible. Why? Because C is equal to mu I plus yi, and C is greater than 0. I'm not going to set C, right, to value equal to 0. So basically, I cannot get that mu I and lambda I is equal to 0. It's a positive value. C. So then I have the second case. When mu I is not equal to 0, what does this tell me? Right? I know that mu I times eta I is equal to 0, so eta I has to be equal to 0. And so I get yi double transpose xi plus b is greater than 1. Okay? Now, when lambda I is not equal to 0, I get this has to be equal to 0. Right? The second part has to be equal to 0. So I get yi double transpose xi plus b is equal to 1 minus eta I. Again, I have 2 cases. Mu I is equal to 0. Mu I is not equal to 0. When mu I is equal to 0, I get that eta I is not equal to 0, so eta I is positive. And I get that yi w transpose xi plus b is less than 1 because eta I is positive. And when mu I is not equal to 0, I get that eta I is equal to 0. Yeah, so that this equality equation holds. So I get that yi w transpose xi plus b is going to be equal to 1 because eta I is equal to 2. Okay. So I have 3 types of points. That's what I'm trying to reach. I have 3 types of points. Points where the distance is greater than 1, points where the distance is less than 1, and points where the distance is equal to 1. Okay? Points where the distance is greater than 1 are what type of points? Are interior points.
Right inside the margin.
Yeah, it's outside the margin, right? And barrel margin, right? They are the anterior points, completely outside the margin, like before. And then I have non-marginal support vectors. These are the ones that cross the margin. So these are the ones that have distance less than 1. And I have marginal support vectors, which are the ones on the margin, yeah, where the distance is equal to 1. So I have 3 types of points: interior points, non-marginal support vectors that are crossing the margin, and marginal support vectors, which are the ones on the margin. I can use any marginal support vector, right? So using this equation to get the value of B, as we did before. All right. So I have 2 types of support vectors as before, right? As we said, marginal support vectors. These are, right, lambda I is greater than 0 and less than C. The eta I is equal to 0. So these are on the margin. And non-marginal support vectors, these are lambda I is equal to C exactly, because I have lambda I is equal to mu I plus, C is equal to lambda I plus mu I, right? And I have eta I is greater than 0, and I get these are internal, like points that cross the margin, yeah? So, and this figure, which ones are the marginal support vectors, which one are the interior points, and which one are the non-marginal support vectors? Marginal is which one? These.
marginal هذول اللي على المارجن.
على
Yes.
المارجن. This is a non-marginal support vector, and these are interior points. Sorry, these are interior points. Okay. Good. So using SVM. So last thing, yes. How do I know? I'm going to talk about this in this slide. Oops. Okay. So when using a hard margin SVM, always ensure data is linearly separable. How? So quadratic program doesn't return a solution. Basically, you write the library and it doesn't return any solution. Yeah, so it runs forever, keeps running. You try it for a while and it doesn't return anything. Yeah, the library doesn't return anything. Or it returns some solution, and then obviously you can use this solution to see if the data is perfectly separated or not. Does it give you 0 in sample error? If it gives you 0 in sample error, then it separates the data linearly. Yeah, it has to separate the data linearly by giving you 0 in sample error. Okay. So for non-linearly separable data, you use either a kernel or a soft margin SVM or both. You decide using validation and set the C, right, the value of the soft margin SVM using validation as well. This is a very important hyperparameter. In the library, you will have only soft margin SVM, so you have to set a value for C. You can set it very large if you want to do hard margin SVM. You can set it, try to reasonable values if you want to do soft margin, and you try with different values of C and C. You can combine, right, soft margin with kernel, right, and see how it performs. Yeah, so basically on validation data as well. Okay, so now we can do the assignment. It's again not difficult. I'll ask Shadi to do a session for you on Monday. Okay, now we're running out of time, so if you have no further questions, we'll stop here.
Sir?
Yes.
In the assignment or in general, so
yeah.
When I'm classifying tweets, if I fit the data only to fit the model to my training data set, so how will it know if while using it if a new English word enters the model? So
typically, this is a good point, right? So typically, it does something sort of smoothing, right? So you either ignore, right, the words that do not appear in your training data, or you do some, you will use some averaging, right, to statistics on it, right? So average values of features for it, right? So if you're using TF-IDF, for instance, you do it on the training data, and then using on validation and test. So it's a good point, but the libraries can handle this. Yeah, so there are techniques that can handle this. Yeah, does this answer your question? But it's a good.
Yes, yeah. Yes, thank you. But like, how can you do it using statistics?